To discuss more about a wave, next I am going to discuss about a sinusoidal wave. And a sinusoidal wave, the terminology is, here I have shown a wave of some oscillation and it is moving along the z direction with velocity v, and where a is the amplitude and this is the wavelength between the trough and trough, the distance, the consecutive distance between two troughs or crust. This is known as the wavelength, and this is the central maximum where at time t is equal to 0, the wave function behaves like this. So mathematically, after some time t, this wave can be represented f of z after some time t. This may be written as a cosine of k z minus vt plus delta. Now, a is the amplitude of this wave, where this term, this is the argument, and this argument is known as the phase. Delta, this is known as the phase constant. So I have written the argument of cosine is called the phase and delta is the phase constant. Notice that z is equal to vt minus delta divided by k. If we put here z is equal to vt minus delta k, then the phase will be equal to 0, because such as k into z minus vt plus delta, I have considered this argument vt minus delta t. So this is the case, and where this vt will cancel with this vt, and further k into minus delta divided by k plus delta, k cancel with k minus delta plus delta, which is equal to 0. It means that this phase is equal to 0 when we consider z is equal to vt minus delta divided by k. It means that if delta is equal to 0, if we consider delta is equal to 0, then the central maximum passing through the origin at time t is equal to 0. It means that when a wave is here, then it is with a small distance with central maximum z is equal to 0. It may have, we can say that this delta divided by k, when it is moving in this direction, then there is some small displacement at the origin. When a wave is moving in this direction, then we can consider this, this will be delta divided by k. More generally, delta divided by k is the distance by which the central maximum of the entire wave is delayed. So this is the case. We also know about the wave number, the k, mathematically 2 pi divided by lambda, and where lambda, which is equal to 2 pi divided by k. At fixed point z, the string vibrates up and down. Then it may have a time period, and this time period we can say that t, which is equal to 2 pi divided by kv, this is the time period, where we can say that the frequency, the relation between the frequency and time period, this is the nu, which is the frequency, which is equal to 1 over t, and then nu, which is equal to putting the value of t, 2 pi divided by kv here, then it equal to kv divided by 2 pi, and then v divided by 2 pi divided by k, which is equal to v divided by lambda. So this is very easy mathematical expression, and then nu, which is equal to v divided by lambda, or v is equal to nu lambda. So this is a very special equation in wave. Similarly, the angular frequency, we can also define the number of radians swept out per unit time. This is known as the angular frequency. And the angular frequency we can write in this form, omega, which is equal to 2 pi nu, where nu is equal to V divided by lambda. And further, if we put the value of lambda, which is equal to 2 pi divided by k, then 2 pi and 2 pi will cancel, and we can have omega, which is equal to kv. So this is omega, which is equal to kv. It means that this wave, this sinusoidal wave, we can write f of z into t, which is equal to a cosine of multiply this kz minus kvt plus delta, where this kv, I have written this in the form of omega. Then f of z into t, which is equal to a cosine of kz minus omega t plus delta. This expression shows that the sinusoidal oscillation of wave number k and angular frequency omega traveling to the right. Now, this is the sinusoidal oscillation of wave number k and angular frequency omega moving or traveling to the left, and we can represent the wave like this. Usually, we consider the sinusoidal wave in complex form. Why we need to write the wave in a complex notation? Because the complex notation, the representation of complex notation, mathematically it is very easy, and one can solve different and complicated mathematics using a complex notation. In view of Euler formula, we can say that e की power iota theta, which is equal to cosine of theta plus iota sine theta. And the sinusoidal wave f of z into t, we can write real of a e की power iota kz minus omega t plus delta. And this means that real, we can pick the real part of this form, because this is equal to a cosine of kz minus omega t plus delta plus iota sine of kz minus omega t plus delta. So I have written this real of this. Real of this means we can pick this term, and this is equal to f of z of t, and this is the sinusoidal wave. If we introduce a complex wave function, further, if we introduce a complex wave, for example, this function f of z into t, this will be equal to a tilde e की power iota kz minus omega t, where the complex amplitude, where a tilde, this is equal to e की power iota delta. If we replace back, we can get the same thing. And here the actual wave function f of zt, which is equal to real of f tilde of z into t. Next, we want to represent the sinusoidal wave in a linear combination. Any wave can be expressed as a linear combination of sinusoidal one. For example, f of zt, which is equal to, we can write this in an integration, and where the amplitude and e की power iota kz minus omega t and dk, a1 of k e की power iota k 1z minus omega t plus a2 tilde k, this is k1, this is k2, and e की power iota k2z minus omega t, and so on. So it means that we can represent a sinusoidal wave in a linear combination as well. We have an example 9.1, and it states that if we have f1 tilde, which is equal to f1 tilde e की power iota and kz minus omega t, and f2 tilde, which is equal to a2 e की power iota kz minus omega t. We have two waves, f1 and f2. Then the linear combination of these two, we can write this in f3 tilde, which is equal to f1 e की power iota kz minus omega t plus a2 e की power iota kz minus omega t. And this f3 must be equal to a3 tilde e की power iota kz minus omega t, which is equal to f1 e की power iota kz minus omega t plus a2 e की power iota kz minus omega t. It means we can neglect this term, and then we have a3, and a3 is actually equal to e की power iota delta 3, which is equal to a1 e की power iota delta 1 plus a2 e की power iota delta 2. In other words, we just add the complex amplitudes. The combined wave still has the frequency and wavelength. And finally, f3 of z into t, this must be a3 and cosine of kz minus omega t plus delta 3. So this will be the final, the combined wave. Uh, we can consider two waves. For example, one wave as in this form. This is F1 and which has amplitude A1. We have another wave like this, which has amplitude. This has amplitude A2. Then the combination of these waves must have different amplitude. So the superposition of these F1 and F2 must have a different amplitude, and we can say that this will be A3. And the phase constant also different with delta 1 and delta 2. Boundary condition. In the previous section, up to now, we didn't consider what will happen when a wave is moving and it reach to the point where there is some boundary condition. What will happen? Then we have to discuss about the reflection and transmission. I have written what will happen to the wave when it reaches to the end. In the previous case, we didn't consider this point. Consider a string is tied on to a second string. We consider here, this is a string. And this string is considered to another string. And here you can see this is a knot. And this string is thick. And this is thin. Then it should be noted that the tension remains the same in both the strings. T remains constant for both strings. But mu we have defined in the last structure. This is the mass per unit length, because the mass per unit length in this string and this string will be different. If I consider this point, the mass per unit length here and the mass per unit length here, then this mass per unit length and this mass per unit length will be different. So it means that mu must be different. If mu is different, then by definition, v, which is equal to t divided by mu under root, the velocity of the wave, and this is equal to t divided by mu. If mu is different, then v must be different. If this increases, this will decreases, and vice versa. Then, if we consider this is a knot, and this is some point where we have joined these two strings, if the wave is moving in this string, this is, we can say that this is the incident wave, and I want to represent this as in the f1 of zt, which is equal to f1 tilde, and this is equal to iota k1 minus k1z minus omega t. And there is some possibility, if I consider this is z is equal to 0, then this wave z is less than 0. Then there is some possibility that some wave is reflected back and some part of the wave is transmitted. There is some possibility. If we have a knot here, then f2 of z into t, which is equal to f1 of tilde and the exponential iota minus k1. This is the same medium because k1, which is equal to 2 pi divided by lambda, this is related to this string, minus omega t. Remember this point. Last time we have discussed that when there is a minus omega t, then this wave is moving from left to right. And whenever this is plus, it means that this is moving to the left. But here I have write down minus k1z, and this remains the same. So it means that if we change this or this will be the same. And now this wave is moving to in this direction, and this is also z is less than 0. Now some part of this wave is transmitted, and we can write f3 of z into t, which is equal to, this must be a2. This is not f1, but this is a2, and this is a3 tilde, and e ki power, this is in this direction, so iota k1 will be different. Here is the k1 in the first in this medium, but in this medium, in this thick string, the kappa will be different. The kappa means wave number will be different. Kappa k2 z minus omega t, and this z is greater than 0. So this is incident. The wave is moving in this direction. This is a reflected wave, and this is a transmitted wave. It should be noted that all the parts of the system are oscillating at the same frequency. So we have considered omega, omega, and omega. Also, wave velocity are different in the two strings, as well as wavelength and wave number, because I have, this is a k1, k1, and this is a k2. Then it means that the wave number k1, which is equal to 2 pi divided by lambda 1, and k2, which is equal to 2 pi divided by lambda 2. Then from this, lambda 1, which is equal to 2 pi divided by k1, and here lambda 2, which is equal to 2 pi divided by k2. So this will be the situation. And we also know that omega is equal to kv, and if omega is the same, then in the first string, in this string, omega, which is equal to k1 v1, and in the second string, there will be the omega will be k2 v2. Then from these two equations, I can write k1 v1, which is equal to k2 v2. And further, If I put the value of K1 and K2 here, then K1 is equal to 2 pi V1 divided by lambda 1, and here K2, which is equal to V2 and 2 pi divided by lambda 2. Then 2 pi and 2 pi will cancel out, and V1 divided by lambda 1, which is equal to V2 divided by lambda 2. This will be the relation. And further, if I some cross multiplication in this equation, then lambda 1 divided by lambda 2, which is equal to lambda 1 divided by lambda 2, then V1 divided by V2. So this will be the expression. Further, one may prefer to consider an incident wave of finite extent. This is the incident wave which is moving in this direction with the v velocity. Then some part of this wave can be reflected back, and some part can be transmitted to the second medium. Then this is the reflected wave and this is the transmitted wave. Then mathematically we can write AI, incident amplitude delta e की power iota k1z minus omega t plus AR, the reflected one, e की power minus k1z minus omega t. And this is the case where z is less than 0. This is z which is equal to 0. This is less than 0. And there also a transmitted wave. This is a transmitted wave with some velocity v2, and at which is at e की power iota k2 z minus omega t. This is z is greater than 0. So this is the case that when a wave is moving in one medium, then there is a chance that it reflected back, and there is a chance that when it can be transmitted. Further, at z is equal to 0, the function f of zt is continuous. There is a concept of continuous and discontinuous. If a wave is totally reflected back in the string, then it means that there is some discontinuity in the medium. And whenever some of the wave is transmitted to the other medium, then it means that there is some continuity in the two medium. Previously, I have considered that we have two strings. This is a thick one, and I have another one. This is a thin one, and there is a knot. If this string is very heavier than this one, let's suppose, then for this thin string, if we want to generate a wave in this string, and this is very heavier, then it means that there is some discontinuity in these two media, and the wave will be reflected totally in this thin string, because this is very heavier than this one. So it means that there is some discontinuity between these two media. But if we have, this is a thick, this is a thin, but this is not more than heavier than this, then it means that some part of the incident wave can be transmitted through this string, and there is some continuity will occur in these two strings. So it means that there is some continuity and discontinuity in the medium. Then let's suppose I have written this f of 0 minus t and f of 0 plus t. If these are equal, f of 0 minus and 0 plus, what is 0 minus and 0 plus? These are two media, and this 0 minus, if I consider this small, this is a 0 minus, and I have written this z is equal to 0 minus the displacement just slightly to the left. This is just slightly to the left because this is z is equal to 0. So this distance is known as 0 minus. Further, z is equal to 0 plus. This the displacement just slightly to the right. So there, this is a very small displacement. This is a small displacement, this one, and this is known as 0 plus. When these two functions are equal, then it means that this is there is a continuity between these two media, and the media there is a continuous uh, 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 and here, if the knot itself is of negligible mass, then the derivative of f must also be continuous. If there is the knot which is some negligible mass, then it means that the change in the function with respect to z will also be equal at z is equal to 0 minus and z is equal to 0 plus. So these two are the boundary conditions. This one, this is the first boundary condition, and this is the second boundary condition. And we can also represent the complex function as well, and the derivative of the complex function as well. Partial f tilde divided by partial z, z is equal to 0 minus, which is equal to this, z is equal to 0 plus. Now we want to apply these two boundary condition and want to discuss about the incident, reflected and transmitted wave. Let's consider this. We have, this is the incident wave, this is the reflected wave, and this is the transmitted wave. And the boundary condition is, the first boundary condition is f of tilde 0 minus t, which is equal to f of tilde 0 plus t. Then what will happen? Z is approximately equal to 0. So if z is equal to 0 here, z is equal to 0 here, z is equal to 0 here. Then from this equation, ai e की power minus iota omega t plus ar e की power minus iota omega t, which is equal to at e की power minus iota omega t. This term will cancel out, and ai plus ar, which is equal to at. This will be the case, and I represent this equation A. Now the second boundary condition is, differentiate this with respect to z and apply the second boundary condition. Then partial f divided by partial z, this will be equal to the this side z as less than 0 and z as greater than 0, this must have the form as, if I differentiate this with respect to z, then ai and iota k1 and e की power iota k1 z minus omega t plus ar, this is minus iota k1 and e की power iota minus k1 z minus omega t, which is equal to this one, and this is at iota k2 and e की power iota k2 z minus omega t, and apply for z is equal to 0. And for z is equal to 0, it means that iota k1 ai and e की power minus iota omega t plus minus, this is minus iota k1 and e की power minus iota omega t, which is equal to iota k2 at and e की power minus iota omega t. Then this term will cancel with this and iota will cancel with iota, and then I can take k1 as common, then ai minus here there is a ar, then ar which is equal to k2 at. And this is, let's suppose this is equation number B. As we have derived two equations A and B, and where AI plus AR which is equal to AT, this is equation A, and K1 AI minus AR which is equal to K2 AT, this is equation B. Now we have two equations and three variables. To solve this, we must have three equations for three variables. But we can solve these two equations in terms of incident wave. We can calculate the reflection and transmission amplitudes in terms of incident amplitude, because one can easily control the incident wave. Then it will be useful to derive AR and AT in terms of AI. So I have written some things. There are two equations A and B, but have three parameters. To solve this, we must represent the reflection and transmission amplitudes in terms of incident amplitude, because one can control the incident amplitude easily. From equation B, we can calculate AT from equation B, then AT which is equal to K1 AI minus AR divided by K2. Put this equation, this term AT in equation A. This is a very simple algebra. AI plus AR which is equal to K1 divided by K2, AI minus AR. Then we must calculate AR, then AR must be in the left hand side and AI must be in the right hand side. So this is a very simple algebra, and AR which is equal to this, and LCM of this, this will become K2 plus K1 divided by K2, and this must be equal to K1 minus K2 divided by K2. And after some steps, AR, which is equal to K1 minus K2 divided by K1 plus K2 AI. So this is the first equation for the amplitude, reflection amplitude, AR. Similarly, putting the value of this AR in this equation, we can easily attain the AT, which is equal to 2K1 divided by K1 plus K2 AI. So these two equations are in terms of incident amplitude. We also know that omega, which is equal to K1 V1 and omega, which is equal to K2 V2, calculate K1 from this and K2 from this. Then in terms of velocities, putting the value of K1, K2 in this equation and this equation, we can get AR, which is equal to V2 minus V1 divided by V1 plus V2, AI, and AT, which is equal to 2V2 divided by V1 plus V2, AI. Now, in complex amplitudes, if we replace A tilde with AR e to power iota delta R and AI tilde AI e to power iota delta I, and similarly AT, which is equal to e to power iota delta T, which is equal to AI e to power iota, then we can represent these two equations like this. Now there are some cases that I want to discuss. One, if mu2 is less than mu1, mass per unit length in the second string, and this is the mass per unit length in the first string, and this is less than this, and we also know that mu, which is equal to T divided by V. This is the expression we already know. Then mu1, which is equal to T divided by this, and mu2, which is equal to T divided by V2. If this is the case, then what will happen to this? Let's see. This is T V2 is less than T V1, and T is the same, then we can say that 1 over V2 is less than 1 over V1 under root. And further, it means that V2 integral is greater than V1 integral, and further V2 is greater than V1. So this is the case. V2 velocity in the string 2 must be greater than the velocity in string 1. And this is the case whenever we have, this is z is equal to 0, and I have a string, this one and this one. This is a string 1 and this is a string 2. And further, this string is lighter than this string. This is heavier. This string is heavier than this one. Then the incident wave, the reflected wave, and the transmitted wave, the phases must remain the same. For this, the delta R, which is equal to delta I, and delta T, this must remains the same. The second case is case 2. Whenever we say that this string, this is heavier and this is a lighter one, then what will happen? String 1 is lighter than this. For this case, V2 is less than V1, and the reflected wave is out of phase, or 180 degree. Then this delta R plus phi, this is 180, which is equal to delta I, which is equal to delta T. This will be the condition. Case 3. Whenever this string is very heavier than this one, this string is much massier as compared to this string, then what will happen? Then AR, which is equal to AI, but there will be a total reflection and there will be a no transmission, then AT must be equal to 0, because this is very heavier than this one, and the wave cannot, and this, for this wave, this knot is discontinuous and the wave can be reflected totally.